Now, after the buckling analysis, the next chapter that we will learn is thermal analysis. Now, thermal analysis is a different topic that we are going to start, in which the body that we are going to analyze is going to be subjected to thermal loads. And there are different types of analysis that we will be performing under thermal analysis. So, let us understand what is thermal analysis first. Thermal analysis is the most important analysis through which a design has to pass before manufacturing. Apart from the structural analysis, where we are understanding the displacements, stresses, deformations, all these things, thermal analysis is also important for a design, because you need to understand whether the design that you are creating will be able to sustain the temperatures that are being induced in the body. So that is why it is also one of the most important tests that a design has to pass through. Thermal analysis is used to analyze the temperature distribution and related thermal quantities. So when we are performing the thermal analysis, we understand what is the maximum or minimum temperature distribution in the design and where exactly in that design it is happening. Apart from the temperature distribution, there are other thermal quantities that we will be analyzing or we will be calculating using the thermal analysis. For example, thermal flux, thermal flow, amount of heat lost or amount of heat gained. So all these are different quantities that we can also calculate using the thermal analysis. Thermal analysis is used in many engineering domains such as automobile, piping, electronic power generation, and many other. So it is not only related to any one specific industry, it can be applied or it is used in many industries such as automobile, piping, or electronic power generation. Whenever a body is subjected to thermal loads such as temperature, internal heat generated, temperature is induced in the body due to the heat transfer. So whenever we have an object, if we have a design and it is subjected to a thermal load, for example temperatures, or internally heat is getting generated in it because of some other input, such as when you, for example, when you charge a mobile battery, you are heating the you are not heating, you are charging your mobile phone using the electricity, but due to the charging, the battery gets heated up due to the heat generated inside it. So that is an example of heat generation, due to which temperature is induced in the body. So we will be learning about what are the different types of heat transfers, because when you talk about temperature induced, it happens because of the heat transfer. Whenever heat gets transferred from one object to the other, temperature is induced. So when we are learning about thermal analysis, we will be also talking about the different types of heat transfers, and we will be seeing some examples using which we will calculate the temperatures, heat lost or heat gain, thermal gradients, or thermal fluxes. So let us talk about the heat transfers first. What are the different types of heat transfers? There are three major types of heat transfers: conduction, convection, and radiation. So let us discuss about conduction first. Conduction is the process of heat transfer between the bodies in contact. Whenever two bodies are directly in contact with each other, you can see the image over here. Just 1 second. Now you can see that whenever two bodies are directly in contact with each other, now this body over here, that is T2, where it is getting heated up at a temperature T2 which is higher than or more than T1. So the heat will flow from higher to lower. So this is an example of conductivity where two bodies are directly in contact with each other. The medium of contact is a solid. Okay. So when you talk about the heat transfer, the formula that we consider in conduction is K A delta T, where K is the thermal conductivity of the material, A is the area of contact, and delta T is the change in temperature. Okay. So this is about conduction. Next is convection. Convection is a process of heat transfer in which the medium of heat transfer is a fluid. When you say fluid, it can be a liquid also or gases also. Fluid does not mean anything has to be liquid. but it can be liquid plus gases also. So there are different examples of convection. For example, when you are heating water using a heating rod, electric heating rod, that is an example of convection. When you keep a cup of tea for some time, the tea becomes cold. That is because the heat from the tea is getting transferred to the outside ambient temperature. So even that is an example of convection. When you talk about convection, the formula that we will use is Q is equal to HA delta T. Now delta T is nothing but it is a difference in temperature, the surface temperature and the ambient temperature. Okay, ambient temperature is nothing but the atmospheric temperature which is surrounding that object. Okay, where Q is the amount of heat transfer, H is the film coefficient. Okay, and delta T is the change in temperature. Now let us talk about radiation. Radiation is a mode of heat transfer in which the heat is transferred through space. Okay. Now whenever the heat is getting transferred in space, we call it as radiation. The best example of radiation will be the sun rays which get transferred to the earth. The other examples can be when you are heating something inside a microwave oven, or the electromagnetic waves, or your light waves. Okay, all these are examples of radiations. Even your X-rays are examples of radiations. Now the formula that we consider, or that is used to calculate the radiation, heat transfer due to radiation, is Q is equal to emissivity into sigma, that represents Stephens-Boltzmann constant, A that is the area, and T raised to 4, hot means whichever medium is hotter, that is going to transfer heat to the colder medium. So it is a temperature difference between the hot medium and the cold medium. Now in this case, the surface emissivity is represented by this symbol over here. Now when you talk about radiations, there are two types of bodies. Whenever a body is being radiated with energy or some rays, if it is a perfectly black body, it will absorb everything that is radiated on it. So the emissivity is it does not radiate anything back, it absorbs everything. So in that case, the emissivity is 1. Okay, but if it is it's not a black body, it is a gray body, then in that case emissivity will be something lesser than 1. So if it is radiation, if you're talking about radiations on a perfectly black body, emissivity becomes 1. So the formula becomes sigma, that is Stephens-Boltzmann constant, area, and T4, that is a temperature difference. Okay, so these are the different types of heat transfers that we need to know before we start with thermal analysis. So the three types of heat transfer are conduction, convection, and radiation. In our syllabus, we are going to talk about conduction problems and convection problems. Then let us talk about the different types of thermal analysis. There are two major types of thermal analysis, that is steady state thermal analysis and transient thermal analysis. When you talk about steady state thermal analysis, in this type of analysis, the temperature acting on the body does not vary with respect to time. That means it is constant throughout the analysis. And when you talk about transient thermal analysis, it is that type of analysis where the temperature acting on the body varies with respect to time. Okay, so we will be seeing both the types when we solve the problems. Okay, so this is about the thermal analysis. We have understood about the basics of thermal analysis. What is thermal analysis? Why we are performing the thermal analysis? What are the outputs that we can calculate when we are performing thermal analysis? And then we have spoken about the heat transfers. Apart from this, there are many other basic definitions that are given in the reference guide. You can just go through that once because they are all basic definitions related to specific heat, emissivity, Stephens-Boltzmann constant, or your film coefficient. There are basic definitions. So kindly go through that once when we start practicing thermal analysis. Okay. Now, in the next video, we will understand some examples on thermal analysis.